Welcome back to Nebula Nights. Tonight, we're embarking on a journey through time itself, traveling backward through 13.8 billion years of cosmic history to witness one of the most profound transformations the universe has ever undergone. We're going to explore the birth of galaxies, those magnificent island universes that populate the cosmos, each one a collection of hundreds of billions of stars, bound together by gravity and swirling through the darkness of space. Picture the universe today. When you look up at the night sky, if you're far enough from city lights, you can see the Milky Way stretching across the darkness like a luminous river. That band of light represents just a fraction of our own galaxy, home to somewhere between 100 billion and 400 billion stars. But our galaxy is just one among countless others. In every direction we look, telescopes reveal galaxies beyond galaxies, stretching away into unimaginable distances. Some appear as elegant spirals with graceful arms sweeping through space. Others are smooth elliptical islands of ancient starlight. Still others are irregular, chaotic assemblages shaped by violent collisions and gravitational encounters. But it wasn't always this way. There was a time when none of this existed. No galaxies, no stars, no planets, no light piercing the darkness. To understand how we got from that primordial state to the rich, complex universe we see today, we need to go back to the very beginning. 13.8 billion years ago, everything that would ever exist burst into being in an event we call the Big Bang. In that first incomprehensibly hot, dense instant, the universe was nothing like the cold, vast expanse we observe today. It was a roiling soup of pure energy, so hot that matter as we know it couldn't exist. Fundamental particles flickered in and out of existence. Space itself expanded faster than the speed of light in a process called inflation, taking a region smaller than an atom and stretching it to astronomical proportions in a fraction of a second. As the universe expanded, it cooled. Within the first few minutes, conditions became suitable for the simplest atomic nuclei to form through a process called Big Bang nucleosynthesis. Protons and neutrons combined to create the nuclei of hydrogen, the simplest element with just one proton. Some formed deuterium, a heavier version of hydrogen with one proton and one neutron. A fraction combined further into helium nuclei with 2 protons and 2 neutrons. An even tinier amount formed lithium. But that was it. The universe was expanding and cooling too rapidly for anything heavier to form. The cosmic recipe at this point was straightforward. Roughly 75% hydrogen, 25% helium, and just trace amounts of lithium and beryllium. This primordial mixture would remain essentially unchanged for hundreds of millions of years. For the next 380,000 years, the universe continued to expand and cool, but it remained opaque. Photons of light couldn't travel freely because they were constantly scattering off the free electrons that filled space. Imagine trying to see through a thick fog, but this fog filled the entire universe. Everything was ionized, meaning atoms hadn't formed yet. Electrons and atomic nuclei existed separately, bouncing around in a hot plasma. Then came a pivotal moment known as recombination. The universe had cooled enough that electrons could finally bind to atomic nuclei without immediately being knocked free again. Neutral atoms formed for the first time. Hydrogen atoms with their single electron orbiting a single proton. Helium atoms with 2 electrons surrounding their 2 protons. This transformation had a profound effect. With electrons now bound to atoms, photons were suddenly free to travel through space without constantly scattering. The universe became transparent. The light from this moment, stretched and cooled by 13.8 billion years of cosmic expansion, still reaches us today as the cosmic microwave background radiation, a faint whisper of that ancient transformation visible in every direction we look. But even though the universe had become transparent, it was about to enter a period of profound darkness. After recombination, the universe consisted of an enormous expanding cloud of neutral hydrogen and helium gas. There were no stars. There were no galaxies. There was no light except for the steadily red-shifting afterglow of the Big Bang itself. Astronomers call this period the Cosmic Dark Ages, and it's a fitting name. For hundreds of millions of years, the universe was genuinely dark, a vast expanse of neutral gas slowly clumping under the influence of gravity. This might sound like an uneventful period, but in reality, it was a time of preparation. The seeds for everything that would come later were being planted. Even in the nearly uniform sea of primordial gas, there were tiny variations in density. These weren't random. They originated from quantum fluctuations in the incredibly early universe that had been stretched to cosmic scales during inflation. Some regions had slightly more matter than others. The differences were minuscule, only about 1 part in 100,000, but they were enough. Gravity is a patient sculptor. It works slowly but inexorably, pulling matter from regions of lower density toward regions of higher density. Over time, these small differences grew. Denser regions attracted more matter, becoming denser still, which made them attract even more matter. This runaway process is called gravitational collapse, and it was happening throughout the Dark Ages on various scales. Small clumps formed first, then merged into larger clumps, building up a hierarchy of structure that would eventually become the cosmic architecture we see today. But there was another player in this cosmic drama, one that we still don't fully understand: dark matter. To understand how the first galaxies formed, we need to understand dark matter. This mysterious substance makes up about 84.5% of all matter in the universe, yet we can't see it. It doesn't emit light, doesn't absorb light, and doesn't reflect light. It doesn't interact with electromagnetic radiation at all. We only know it exists because of its gravitational effects. The evidence for dark matter is overwhelming. When astronomers measured the rotation speeds of spiral galaxies in the 1970s, they discovered something puzzling. The stars at the outer edges of these galaxies were moving far too fast. According to the laws of gravity, they should have been flung out into intergalactic space. The only explanation was that these galaxies contained far more mass than we could see, an invisible halo of matter holding everything together. Similar observations in galaxy clusters, combined with gravitational lensing effects, where massive objects bend the path of light passing by them, all pointed to the same conclusion. Most of the matter in the universe is dark matter. But what does dark matter have to do with galaxy formation? Everything, it turns out. During the Dark Ages, while ordinary matter in the form of hydrogen and helium gas was cooling and becoming neutral, dark matter was already hard at work. Unlike ordinary matter, dark matter doesn't interact with radiation, which meant it could start clumping together earlier. Dark matter particles, whatever they might be, began gathering into structures under their own gravitational attraction. These dark matter structures formed along narrow filaments, creating a cosmic web that still defines the large-scale structure of the universe today. At the intersections of these filaments, dark matter accumulated in dense concentrations called dark matter halos. Think of these halos as gravitational wells, invisible pockets of mass scattered throughout the young universe. They were the foundation upon which galaxies would be built. As dark matter halos grew more massive, their gravitational pull became stronger. They began attracting the hydrogen and helium gas that filled the spaces between them. Ordinary matter fell into these invisible halos, pulled by gravity toward their centers. The gas compressed as it fell inward, heating up from the compression. In the deepest parts of the most massive halos, conditions were becoming suitable for something remarkable: the birth of the first stars. This is the crucial insight about galaxy formation. Galaxies didn't form in isolation from pristine gas clouds scattered randomly through space. They formed at specific locations, precisely where dark matter had already congregated and created the gravitational scaffolding necessary to hold them together. Without dark matter, the ordinary matter in the universe couldn't have clumped together quickly enough to form galaxies in the time available. The expansion of the universe would have pulled everything apart before galaxies could form. Dark matter provided the gravitational glue that made structure formation possible. The smallest dark matter, halos capable of forming stars, had masses of around 1 million times the mass of our Sun. These were the first sites of star formation in the universe. Larger halos with masses of 10 million to 100 million solar masses became the nurseries for the first galaxies. And the most massive halos, containing billions of solar masses, would eventually host the largest galaxy clusters we see today. The cosmic web of dark matter created a template. Galaxies would form at the nodes where filaments intersected. They would grow by accreting gas from their surroundings and by merging with other galaxies. Over billions of years, small galaxies would combine into larger ones, building up the massive galaxies we see in the present-day universe through a hierarchical assembly process. But before any of this could happen, the universe needed its first stars. Somewhere between 150 million and 300 million years after the Big Bang, inside the first dark matter, halos, hydrogen gas was accumulating and compressing. As the gas fell deeper into these gravitational wells, it heated up from the compression. But for stars to form, the gas needed to cool down enough that gravity could compress it further without the internal pressure pushing it back out. This is where the first challenge appeared. In the modern universe, star formation is aided by the presence of heavier elements like carbon, oxygen, and nitrogen. These elements are incredibly efficient at radiating away heat, allowing gas clouds to cool and collapse. But the early universe had no such elements. The only cooling mechanism available was molecular hydrogen, two hydrogen atoms bonded together, and it wasn't very efficient. The gas could only cool to about 200 degrees Kelvin, which is cold by human standards, but actually quite warm for star formation. This high temperature had a profound effect on the first stars. When gas is warmer, it resists compression more strongly, which means a larger mass is needed before gravity can overcome the pressure and form a star. As a result, the very first stars, which astronomers call population 3 stars, were enormous by modern standards. Computer simulations suggest they ranged from 30 to 300 times the mass of our Sun, with some models predicting that a few might have grown even larger, perhaps reaching 1,000 solar masses. These first stars would have been spectacular objects. Because of their tremendous mass, they would have been incredibly hot, with surface temperatures exceeding 80,000 degrees Celsius, compared to our Sun's relatively modest 5,500 degrees. They would have shone with a brilliant blue-white light, and they would have been astonishingly luminous, outshining our Sun by factors of millions or even billions. But their glory was brief. Massive stars burn through their nuclear fuel at prodigious rates. While our Sun will shine for about 10 billion years, these first stars would have exhausted their fuel in just a few million years. They lived fast and died spectacularly, and in death, they transformed the universe. When a massive star exhausts the hydrogen fuel in its core, it begins fusing heavier elements. Hydrogen fuses into helium, then helium into carbon and oxygen, then those into neon, magnesium, silicon, and so on, building up a layered structure like an onion. This process continues until the core is made of iron. Iron is special because it marks the end of the line. Fusing iron doesn't release energy, it consumes it. Without energy to support it against gravity, the core collapses catastrophically. For the most massive population 3 stars, this collapse triggered explosions of unimaginable violence called pair instability supernovae. These blasts were so powerful, they completely destroyed the star, leaving nothing behind. Other population 3 stars ended in core collapse supernovae. which could leave behind a neutron star or a black hole as a remnant. Either way, these stellar deaths served a crucial purpose. They created and dispersed heavy elements for the first time. Inside these dying stars, nuclear reactions forged carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements that hadn't existed before. When the stars exploded, they blasted these newly created elements into the surrounding gas. This was the universe's first metallicity, its first contamination with elements heavier than hydrogen and helium. And this contamination would fundamentally change how future stars formed. Gas enriched with even tiny amounts of heavier elements could cool more efficiently. This meant the next generation of stars could form at lower temperatures and lower masses. Population 2 stars, as astronomers call them, had a much wider range of masses. Some were still quite large, but many were more modest, similar to stars we see today. And unlike population 3 stars, which formed entirely from primordial gas, population 2 stars contained the ashes of their predecessors. But the first stars did something else equally important. They ended the Dark Ages. When the first population 3 stars ignited, they didn't just shine invisible light. Being extraordinarily hot, they produced copious amounts of ultraviolet radiation. Photons energetic enough to ionize hydrogen atoms by knocking their electrons free. Each star was surrounded by an expanding bubble of ionized gas, carving out a pocket of plasma in the neutral hydrogen that filled the universe. At first, these ionized bubbles were small and isolated, tiny beacons in an otherwise dark cosmos. But as more and more stars formed, more bubbles appeared. They grew, expanded, and eventually began overlapping. This process, called the epoch of rhionization, marked the universe's transformation from a neutral, opaque state back to an ionized, transparent one. The timeline of rhionization is still being refined, but the broad picture is clear. It began somewhere around 150 to 200 million years after the Big Bang, when the first stars formed. It proceeded gradually as more stars and proto-galaxies emerged. By about 1 billion years after the Big Bang, the universe was mostly rhionized, though some pockets of neutral hydrogen persisted in the densest regions. This wasn't an instantaneous phase change, but rather a gradual, patchy process that unfolded over hundreds of millions of years. Early on, most of the intergalactic medium remained neutral, with only small ionized bubbles around the first sources of light. These bubbles were initially quite small, perhaps just a few hundred light years across. But as the universe aged and more ionizing sources appeared, the bubbles grew larger and more numerous. Eventually, they began to overlap, creating larger regions of ionized gas. By the time the universe was 600 million to 1 billion years old, these ionized regions had permeated most of space, and rhionization was essentially complete. The sources responsible for rhionization were probably a combination of different objects. The first massive stars certainly contributed, pouring ultraviolet photons into their surroundings before dying in spectacular supernovae. But galaxies, collections of thousands or millions of stars, were likely the dominant contributors. Small galaxies forming in the first few 100 million years after the Big Bang would have been particularly efficient at allowing their ultraviolet light to escape into intergalactic space. Unlike large, mature galaxies, where most ionizing radiation is absorbed by gas and dust before it can escape, these early galaxies were small, turbulent systems with lower densities, allowing their light to break free and ionize the surrounding medium. There's also evidence that the first black holes played a role. When gas falls into a black hole, it doesn't go straight in, but rather forms a swirling disk around it, heating to tremendous temperatures and emitting intense radiation. These early black holes and their surrounding accretion disks would have been powerful sources of ionizing photons. The epoch of rhionization had lasting effects on galaxy formation. The ultraviolet radiation that ionized the intergalactic medium also heated it, raising its temperature by thousands of degrees. This heating made it harder for small, dark matter halos to attract and hold on to gas. Low-mass halos that might have formed dwarf galaxies found themselves unable to accrete enough gas to continue forming stars. This feedback mechanism may explain why we see fewer small galaxies in the universe than the simplest models predict. The reionization process effectively shut down star formation in the smallest structures, focusing subsequent galaxy growth into larger systems. The transition from the Dark Ages to cosmic dawn, from a neutral universe to an ionized one, from darkness to light, was one of the most dramatic transformations in cosmic history. It set the stage for the emergence of galaxies as we know them. The line between a collection of stars and a galaxy is somewhat fuzzy, but astronomers generally consider the first true galaxies to have appeared between 180 million and 400 million years after the Big Bang. These weren't the grand spiral or massive elliptical galaxies we see in the present universe. They were small, irregular systems, dwarf galaxies by modern standards, containing perhaps a few million to a few tens of millions of stars. These first galaxies formed in dark matter halos with masses of tens to hundreds of millions of times the Sun's mass. Gas fell into these halos, compressed, fragmented, and formed stars. The early galaxies were remarkably compact, often just a few hundred to 1,000 light-years across, far smaller than the Milky Way's 100,000 light-year diameter. They were also incredibly active, converting gas into stars at rates far exceeding what we see in most modern galaxies. This intense star formation made them surprisingly bright for their size. The first galaxies were fundamentally different from galaxies today in several ways. They contained very few heavy elements, just whatever had been produced by the first generation or two of stars. Their stellar populations were extremely young, with average ages of just a few million to a few tens of millions of years. They were also quite gas-rich, with large fractions of their mass still in the form of hydrogen and helium rather than stars. This abundant gas supply fueled their vigorous star formation. The structure of these early galaxies was also different. They lacked the organized spiral patterns or smooth elliptical forms we see today. Instead, they were irregular and clumpy, with star formation concentrated in bright knots scattered throughout. This irregular structure likely resulted from the turbulent conditions in the early universe. Gas flowing into these galaxies was hot and chaotic, without the smooth, organized patterns that develop in more mature systems. As these first galaxies formed and evolved, they weren't isolated. They existed in a universe that was much smaller and denser than today, which meant galaxies were closer together. Interactions and mergers were common. Two small galaxies might collide and merge into a larger one, or a small galaxy might be disrupted by the gravitational pull of a larger neighbor, having its stars and gas stripped away and incorporated into the larger system. This hierarchical assembly process, where small structures merge to form larger ones, is a fundamental feature of how galaxies grow in a universe dominated by dark matter. The dark matter halos that hosted the first galaxies were themselves products of smaller halos merging together. As halos grew through mergers, their galaxies grew as well. Over time, through countless mergers and through the continuous accretion of fresh gas from the intergalactic medium, these modest first galaxies would evolve into the diverse population of galaxies we see today. By the time the universe was about 400 million years old, a significant population of these early galaxies had formed. They dotted the cosmic landscape, glowing islands of light in what was still a largely dark universe. Each one was a factory for producing stars and heavy elements, contributing to the ongoing chemical enrichment of the cosmos. And each one would play a role in the great cosmic story that was only beginning to unfold. The first billion years of the universe saw rapid galaxy formation and evolution. Small galaxies emerged, grew, merged, and in some cases were disrupted. Star formation rates peaked at about 2 to 3 billion years after the Big Bang, an era when the universe was at its busiest in terms of creating new stars. After that peak, galaxy formation and star formation both gradually declined. Today, 13.8 billion years after the Big Bang, the universe forms new stars at only a fraction of the rate it did during that ancient heyday. For decades, astronomers dreamed of seeing these first galaxies directly. But they faced an enormous challenge. These galaxies are incredibly distant, and the light from them has been traveling toward us for more than 13 billion years. During that journey, the universe has expanded dramatically. This expansion stretches the wavelengths of light, shifting visible and ultraviolet light from these galaxies into the infrared part of the spectrum through a process called redshift. The more distant an object is, the more its light has been stretched, and the more dramatically it's been shifted to longer wavelengths. Ground-based telescopes struggle to observe this ancient light because Earth's atmosphere blocks much of the infrared spectrum. The Hubble Space Telescope could see some early galaxies, but it was limited in how far back in time it could look. What was needed was a telescope specifically designed to observe in the infrared, with a mirror large enough to collect light from the faintest, most distant objects, and the sensitivity to detect them despite their extreme faintness. The James Webb Space Telescope, launched in December 2021, was built precisely for this purpose. With its 6.5-meter mirror and suite of infrared instruments, Webb can detect light from galaxies that formed just a few 100 million years after the Big Bang. Since beginning science operations in summer 2022, it has revolutionized our understanding of early galaxy formation. One of Webb's most remarkable discoveries came from the JWST Advanced Deep Extragalactic Survey, known as JADES. This program dedicates nearly 800 hours of telescope time to studying the early universe, making it one of the most ambitious observing programs ever undertaken. And it has delivered spectacular results. In May 2024, the JADES team announced the discovery of JADES GS Z14-0, the most distant galaxy confirmed at that time. This galaxy existed just 290 million years after the Big Bang, placing it firmly in the first 3% of cosmic history. To put this in perspective, when the light we see from this galaxy began its journey toward Earth, the universe was younger than the universe is now older. The galaxy itself is surprisingly large and bright for such an early time, stretching more than 1,600 light years across and shining with the light of young, massive stars. Most remarkably, Webb's instruments detected oxygen in this galaxy, which means that at least one earlier generation of stars must have already lived and died to produce that element. Even more recently, in late May 2025, astronomers announced the discovery of an even more distant galaxy, nicknamed MOEM Z14, existing just 280 million years after the Big Bang. This galaxy is about 50 times smaller than the Milky Way, but it shows clear signs of vigorous star formation. Emission lines in its spectrum indicate the presence of both carbon and nitrogen, heavier elements that could only have been created in earlier generations of stars. This suggests an even older population of galaxies must exist, though they haven't been detected yet. Another fascinating discovery is galaxy GNZ11, observed when the universe was just 430 million years old. Webb found evidence that this galaxy hosts a rapidly growing supermassive black hole at its center, already containing millions of times the Sun's mass despite the early epoch. The galaxy also shows powerful winds being blown out from its center, likely driven by the black hole's activity. Even more intriguing, Webb may have detected a clump of pristine gas in the halo surrounding GNZ11, possibly showing the first direct evidence of population 3 stars forming. These observations have revealed something unexpected about early galaxies. Many of them are significantly brighter and more massive than theoretical models predicted. Before Webb, most simulations suggested that galaxies in the first few 100 million years after the Big Bang would be small, faint proto-galaxies, barely detectable even with the most powerful telescopes. Instead, Webb is finding a population of surprisingly bright, mature-looking galaxies that seem to have formed stars and assembled mass much faster than thought possible. This tension between theory and observation doesn't mean our models are completely wrong, but it does suggest we're missing something. Perhaps star formation was more efficient in the early universe. Perhaps the initial density fluctuations that seeded galaxy formation were slightly stronger than we thought. Perhaps black holes played a larger role than expected in heating the early galaxies and making them appear brighter. Or perhaps the answer involves some combination of these factors. One particularly important finding is that some of these apparently massive early galaxies are actually less massive than they first appeared. The culprit is black holes. In some cases, what looks like a large massive galaxy is actually a smaller galaxy with an active black hole at its center. The black hole's accretion disk produces so much light that it outshines all the galaxy's stars combined, making the galaxy appear much more massive and luminous than it actually is. This discovery has helped resolve some of the tension, though not all of it. There are still more bright galaxies in the early universe than models predict, even after accounting for active black holes. Webb has also discovered a galaxy with unusual properties that might represent a transitional phase in galaxy evolution. Galaxy GS NDG 9422, observed about 1 billion years after the Big Bang, shows a peculiar spectrum where the gas appears to outshine the stars. This suggests the galaxy is in the midst of an intense burst of star formation, with its gas clouds being heated to extreme temperatures by an abundance of very hot, massive stars. This might be a snapshot of how galaxies transition from having mostly pristine gas to becoming star-dominated systems. Perhaps one of the most exciting aspects of Webb's observations is the Firefly Sparkle galaxy, a system observed as it existed just 600 million years after the Big Bang. This galaxy is particularly interesting because it has a mass similar to what the Milky Way probably had at the same stage of its development. While most early galaxies Webb has detected are much more massive, Firefly Sparkle might be more representative of typical galaxy formation. It consists of 10 distinct star clusters, each visible as a separate point of light, giving astronomers an unprecedented look at the building blocks of galaxy assembly. The galaxy is also interacting with 2 companion galaxies nearby, providing insight into how mergers and interactions shape galaxy evolution. Webb's discoveries are still accumulating. Every new deep field observation reveals more distant galaxies, pushing back our view of cosmic dawn. But these observations do more than just find distant objects. They're teaching us about the physical processes that govern galaxy formation. By measuring the brightness, colors, sizes, and spectral features of early galaxies, astronomers can determine their star formation, rates, ages, masses, chemical compositions, and the properties of their black holes. This wealth of data is refining our understanding of how galaxies form and evolve in ways that wouldn't have been possible even a decade ago. While those first galaxies were small and irregular, the present-day universe hosts an enormous diversity of galaxy types. Understanding this diversity requires understanding how galaxies grow and transform over billions of years. The most iconic type of galaxy is the spiral galaxy, and our own Milky Way falls into this category. Spiral galaxies are characterized by a flat rotating disk of stars, gas, and dust, with spiral arms winding outward from a central bulge. They're often stunningly beautiful, displaying elegant pinwheel-like patterns that seem to suggest organized, graceful motion. About 60% of all large galaxies are spirals, making them the dominant type in the universe. The central bulge of a spiral galaxy contains older stars, typically population 2 stars that formed early in the galaxy's history. The disk, by contrast, contains stars of all ages, including young, hot blue stars, born recently from the gas and dust that permeates the disk. The spiral arms themselves aren't permanent features made of specific stars. Instead, they're density waves, regions where stars, gas, and dust are temporarily compressed as they orbit the galactic center. New stars tend to form along these density waves where the gas is compressed, which is why the arms appear bright and blue. They're traced by young, luminous stars. Many spirals, including our Milky Way, are actually barred spirals. In these galaxies, the central bulge is crossed by an elongated bar of stars, and the spiral arms emerge from the ends of this bar rather than directly from the central bulge. About 2/3 of all spiral galaxies show this barred structure. The presence of a bar is thought to indicate a mature galaxy, one that has had time to develop this organized feature. Spiral galaxies are actively forming stars, often at modest but steady rates. They contain substantial amounts of gas and dust, the raw materials for new stars, and they can continue forming stars for billions of years. They're dynamic systems, with stars orbiting the center in organized, nearly circular paths, all moving in roughly the same direction like cars on a cosmic highway. Elliptical galaxies present a stark contrast. These galaxies range from nearly perfect spheres to elongated football shapes. They lack spiral arms, lack organized disks, and show very little structure at all. They consist almost entirely of old stars in random orbits, with very little gas or dust remaining. Because they lack the raw materials for new star formation, ellipticals form very few new stars, which has earned them the informal nickname of red and dead galaxies. They appear red because their light is dominated by old, cool stars rather than young, hot blue ones. Elliptical galaxies span an enormous range in size and mass. Dwarf ellipticals contain just a few tens of millions of stars and might be only a few thousand light years across. These are probably the most common type of galaxy in the universe, though their faintness makes them hard to detect. At the other extreme, giant ellipticals can contain trillions of stars and span hundreds of thousands of light years. These galactic behemoths are the most massive galaxies in the universe, often found at the centers of large galaxy clusters. The formation of elliptical galaxies is intimately tied to galaxy mergers. When two spiral galaxies collide, their organized disk structures are disrupted. Stars and gas get flung about by gravitational interactions. The merger can trigger intense bursts of star formation as gas clouds collide and compress. Eventually, after multiple orbits and much chaos, the two galaxies settle into a single, larger system. The merger process scrambles the ordered orbits that characterize the original spirals, producing the random orbital structure typical of ellipticals. If the merging galaxies were gas-rich spirals, the merger-triggered starburst might consume most of the remaining gas, leaving an elliptical with little fuel for future star formation. Evidence supports this merger origin for ellipticals. The stars in elliptical galaxies are typically older than those in spiral disks, suggesting they formed during ancient bursts of star formation. Ellipticals are more common in dense galaxy clusters, where interactions and mergers are frequent. And computer simulations of galaxy collisions successfully produce elliptical-like systems from spiral progenitors. In the early universe, when galaxies were closer together and mergers were more common, ellipticals were less abundant, which makes sense if they form from mergers that take time to occur. There's a third category: irregular galaxies. These are galaxies that don't fit neatly into either the spiral or elliptical categories. They lack organized structure, appearing instead as chaotic assemblages of stars, gas, and dust. Some irregulars are small, dwarf galaxies that never developed significant structure. Others are the products of gravitational interactions, or mergers that have disrupted their original forms. The large and small Magellanic Clouds, satellite galaxies orbiting the Milky Way, are examples of irregular galaxies. They are close enough that we can study them in detail, revealing complex histories of past interactions with our galaxy. There's also an intermediate type worth mentioning: lenticular galaxies. These have characteristics of both spirals and ellipticals. Like spirals, they have a disk and a central bulge. But like ellipticals, they have little gas and dust and show minimal spiral structure or active star formation. They're sometimes called S-Giro galaxies, and they might represent a transitional stage in galaxy evolution. Perhaps spirals that have exhausted their gas supply, or been stripped of gas through interactions with other galaxies. This diversity of galaxy types isn't static. Galaxies can change type over their lifetimes. A spiral might collide with another spiral and become an elliptical. A spiral might fall into a large galaxy. Cluster have its gas stripped away by interactions with hot cluster gas and transform into a lenticular. Even isolated spirals can evolve, changing their spiral patterns, developing or losing bars, and adjusting their star formation rates based on their gas supply and internal dynamics. The early universe was dominated by small, irregular proto-galaxies. Through mergers and accretion, these built up into larger systems. The first large galaxies to form were probably disk galaxies, spirals that assembled from the merger of smaller systems. As the universe aged and more mergers occurred, more ellipticals appeared. Today's mix of galaxy types reflects 13.8 billion years of cosmic evolution, with each type telling part of the story of how galaxies form, interact, and transform. The relationship between galaxy type and environment is also revealing. In the sparse regions of space between galaxy clusters, spirals dominate. In dense galaxy clusters, ellipticals and lenticulars are more common. This environmental dependence suggests that a galaxy's surroundings influence its evolution. In clusters, high-speed encounters can strip gas from spirals, strangling their star formation and transforming them into quiescent systems. The hot gas that fills galaxy clusters can also sweep the cooler gas out of galaxies that move through it, removing their fuel for making stars. At the heart of nearly every large galaxy lies a supermassive black hole, an object containing millions to billions of times the Sun's mass compressed into a region smaller than our solar system. The relationship between galaxies and their central black holes is one of the most intriguing puzzles in astrophysics, and understanding how these black holes formed and grew in the early universe is crucial to understanding galaxy evolution. The first black holes probably formed from the deaths of massive population, 3 stars. When a star more than about 25 times the Sun's mass dies, its core collapses to form a black hole. For the most massive population 3 stars, some reaching 100 or even 300 solar masses. This process would create black holes containing tens to perhaps 100 times the Sun's mass. These stellar mass black holes were the seeds. But how do you get from a black hole containing 100 solar masses to one containing 10 million or 1 billion solar masses? The timescale is surprisingly short. Some quasars, galaxies with extraordinarily luminous active galactic nuclei powered by supermassive black holes, have been detected just 600 to 800 million years after the Big Bang. These objects already contain black holes with masses of hundreds of millions or even billions of solar masses. Growing from 100 solar masses to 1 billion solar masses in less than 1 billion years is a formidable challenge. Black holes grow primarily by accreting matter. When gas falls toward a black hole, it forms a swirling accretion disk. The material in this disk gradually spirals inward, heating to extreme temperatures through friction and releasing enormous amounts of energy in the process. In fact, accretion onto a black hole is the most efficient energy production mechanism known in the universe. converting up to 10% of infalling matter's mass directly into energy according to Einstein's famous equation. For comparison, nuclear fusion in stars converts less than 1% of mass into energy. But there's a limit to how fast a black hole can grow through accretion. As matter falls in and releases energy, some of that energy pushes back on the infalling material. This creates a balance point called the Eddington limit, beyond which the outward radiation pressure exceeds the inward gravitational pull, and accretion effectively stops. For a black hole accreting at the Eddington limit, its mass increases exponentially with a doubling time of about 45 million years, starting from 100 solar masses and growing at the Eddington limit for 800 million years. A black hole could reach roughly 100 million solar masses. That's impressive growth, but it's not quite enough to explain the most massive black holes seen in the earliest quasars. This has led astronomers to consider several possibilities. Perhaps the seed black holes were more massive than we thought. Instead of forming from stellar collapse, perhaps they formed through the direct collapse of massive gas clouds in the early universe. Under certain conditions, a cloud of primordial gas could become unstable and collapse directly into a black hole without first forming a star, creating seeds with masses of 10,000 to 100,000 solar masses. Starting from such massive seeds would make reaching 1 billion solar masses much easier. Another possibility is that black holes in the early universe somehow grew faster than the Eddington limit suggests. If accretion was particularly efficient, perhaps through geometrically thick accretion flows that allowed more matter to fall in, or if the accretion happened in brief but intense bursts, then growth rates could have exceeded theoretical predictions. There's also evidence that mergers between black holes contributed to their growth, particularly in dense environments where multiple proto-galaxies were coming together. Recent observations by the James Webb Space Telescope have provided new insights into this puzzle. Webb has discovered numerous active galactic nuclei in the early universe, more than previously expected. Some of these are in galaxies that appear surprisingly small for their black hole masses, suggesting a different relationship between black holes and their host galaxies in the early universe compared to today. In the modern universe, there's a tight correlation between a galaxy's central black hole mass and the mass of its stellar bulge. But in the early universe, this relationship might have been different, with black holes forming and growing before their host galaxies had fully assembled. One particularly intriguing finding is that many early galaxies show signs of black hole feedback, where energy from the accreting black hole drives powerful winds that blow gas out of the galaxy. This process can both suppress star formation by removing the raw material for making stars, and trigger star formation by compressing gas as the wind sweeps through it. This feedback creates a self-regulating mechanism that may explain why the relationship between black holes and galaxies is so tight today. As a black hole grows, its feedback becomes stronger, eventually limiting both its own growth and the galaxy's star formation. Over time, this process establishes an equilibrium where the black hole mass and galaxy mass evolve together. The role of supermassive black holes in galaxy evolution extends beyond just growing at galaxy centers. When two galaxies merge, their central black holes eventually sink to the center of the merged system and orbit each other. Over time, interactions with stars and gas cause them to lose energy and spiral inward, eventually merging into a single, more massive black hole. This process releases tremendous amounts of energy in the form of gravitational waves, ripples in space-time itself. While we haven't yet detected gravitational waves from supermassive black hole mergers, future space-based detectors should be able to observe them, providing a new window into understanding how these objects grow. The supermassive black holes at galaxy centers also influence their surroundings in other ways. Jets of material launched from the regions around the black hole can extend for millions of light years, heating the gas in galaxy clusters and affecting star formation on enormous scales. Radio observations reveal these jets as bright lobes extending far beyond the visible galaxy. The energy they inject into their surroundings can prevent gas from cooling and falling back into galaxies, regulating star formation across an entire galaxy cluster. The discovery that supermassive black holes were already massive by the time the universe was less than 1 billion years old suggests that black hole formation and growth were remarkably efficient processes in the early universe. The dense, gas-rich conditions, the frequent galaxy interactions, and possibly more efficient accretion mechanisms all contributed to rapid black hole growth. Understanding exactly how this occurred remains one of the major challenges in understanding early galaxy evolution. But ongoing observations with Webb and other telescopes are beginning to provide answers. While individual galaxies are spectacular, stepping back to look at the universe on its largest scales reveals an even more remarkable structure. Galaxies are not randomly distributed through space. Instead, they're organized into an enormous cosmic web, a network of filaments, sheets, nodes, and voids that spans the observable universe. This structure traces back to those tiny density fluctuations in the early universe. Where the primordial gas was slightly denser, dark matter began accumulating. These dark matter concentrations attracted more matter, growing through gravitational collapse. But gravity doesn't just pull matter into spherical clumps. The initial pattern of density fluctuations had structure, with regions of higher and lower density arranged in a complex three-dimensional pattern. As matter flowed along the gravitational gradients created by this pattern, it naturally collected along filaments and sheets, creating the cosmic web. On the larger scales, the structure consists of several key components. Galaxy clusters represent the nodes of the web, locations where multiple filaments intersect. These are the most massive gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, along with enormous quantities of hot gas and dark matter. The total mass of a large galaxy cluster can exceed 1,000 trillion times the Sun's mass, with dark matter accounting for about 85% of that total, hot gas about 12%, and stars and galaxies only about 3%. Filaments connect these clusters, forming the strands of the cosmic web. Galaxies flow along these filaments toward the clusters, like beads sliding along strings. The filaments themselves can be enormous, stretching for hundreds of millions of light years. Recent observations have even detected the faint glow of hydrogen gas within these filaments, proving they're not empty space but contain substantial amounts of matter. Between the filaments lie the voids, enormous regions of space that are relatively empty. These voids can be 300 million light years or more across, containing very few galaxies. They're not completely empty, but their density is much lower than average, perhaps 10% of the mean cosmic density. The galaxies that do exist in voids tend to be small, faint dwarf systems. This web-like structure is a natural consequence of gravitational collapse in a universe dominated by dark matter. Computer simulations that track the evolution of dark matter under gravity, starting from initial conditions based on observations of the cosmic microwave background, produce structures that look remarkably similar to what we observe. The simulations create the same filamentary network, the same clustering of matter at filament intersections, and the same large voids. The cosmic web influences galaxy evolution in profound ways. Galaxies in clusters experience frequent interactions and mergers. The hot gas that fills galaxy clusters can strip cooler gas from galaxies that move through it, a process called ram pressure stripping. This removes the fuel for star formation, transforming gas-rich spirals into gas-poor lenticulars and ellipticals. The dense environment also increases the chances of tidal interactions, where the gravitational pull of neighboring galaxies distorts shapes and can even rip stars away. Galaxies in filaments are also affected by their environment, though less dramatically than those in clusters. They experience more interactions than isolated field galaxies, but fewer than cluster galaxies. The gas flowing along filaments can be accreted by galaxies, providing fuel for ongoing star formation. Filament galaxies represent an intermediate stage, neither as isolated as field galaxies nor as environmentally affected as cluster galaxies. The voids, despite their low density, also leave their mark. Galaxies in voids evolve in relative isolation, experiencing few mergers or interactions. They tend to be smaller, gas-rich spirals with ongoing star formation. The low density of their surroundings means they accrete little additional gas from the intergalactic medium, growing primarily through internal star formation, rather than mergers or accretion. One of the most impressive demonstrations of the cosmic web came from the Sloan Digital Sky Survey, which mapped the positions of millions of galaxies. When astronomers plotted these galaxies in 3 dimensions, the web-like structure became immediately apparent. The famous galaxy map, images showing slices through the universe, reveal the filaments and voids clearly. Some specific structures have become famous, like the Sloan Great Wall, a cosmic filament stretching for about 1.4 billion light-years, making it one of the largest known structures in the universe. More recent surveys have pushed even deeper, mapping the cosmic web out to greater distances and earlier times. The DESI survey, which began operations in 2021, aims to map 35 million galaxies and quasars, creating the most detailed 3-dimensional map of the universe ever made. These surveys not only reveal the structure of the cosmic web, but also allow astronomers to measure how that structure has evolved over time, providing crucial tests of our cosmological models. The cosmic web also affects the properties of the intergalactic medium, the diffuse gas that fills the space between galaxies. In the densest regions, along filaments and in clusters, this gas is heated to millions of degrees and emits X-rays. In voids, it remains cooler and is much harder to detect. The ionization state of this gas, its temperature, and its density all vary depending on location within the cosmic web. Looking back to the early universe, we can trace the emergence of the cosmic web. In the first few 100 million years after the Big Bang, the structure was just beginning to form. Small, dark matter halos were condensing at the intersections of what would become filaments. The first galaxies formed in these halos. Over time, as more structure formed and gravity pulled matter together, the web became more pronounced. By about 2 billion years after the Big Bang, the basic structure of the cosmic web was in place, though it has continued to evolve and become more defined as time passes. The cosmic web provides the framework within which all galaxies form and evolve. It determines where galaxies form, how they interact, what environment they experience, and ultimately what type of galaxy they become. Understanding the cosmic web is therefore essential to understanding galaxies, and understanding the formation of the cosmic web requires understanding the role of dark matter, the initial density fluctuations from the early universe, and the way gravity shapes structure over cosmic time. Stepping back to look at the full sweep of cosmic history, from the Big Bang to the present day, reveals an epic story of transformation. The universe has passed through several distinct eras, each characterized by different physical processes and dominant phenomena. The first era, from the Big Bang until recombination at 380,000 years, saw the formation of the primordial elements and the establishment of the initial density fluctuations that would seed all future structure. This was a hot, dense, rapidly expanding universe where matter and radiation were tightly coupled. The Dark Ages followed, lasting from recombination until the first stars formed somewhere around 150 to 200 million years after the Big Bang. During this time, the universe was neutral, dark, and relatively uneventful on the surface. But beneath that apparent calm, dark matter was accumulating into halos, setting the stage for what was to come. Cosmic dawn arrived when the first population 3 stars ignited, ending the Dark Ages and beginning the epoch of reionization. This era, from about 150 million to 1 billion years after the Big Bang, saw the formation of the first stars, the first galaxies, and the transformation of the universe from neutral to ionized. It was a tumultuous time of rapid change and intense activity. Following re-ionization came a period of vigorous galaxy assembly and star formation. From about 1 to 3 billion years after the Big Bang, the universe was at its most active. Star formation rates peaked. Galaxies were forming, merging, and interacting at high rates. Quasars were common, indicating numerous actively accreting supermassive black holes. The cosmic web was becoming well-defined. This was the era when many of the most massive galaxies in the universe formed most of their stars. By about 3 billion years after the Big Bang, the universe entered a more mature phase. Star formation rates began declining from their peak. Large spiral galaxies were becoming common. The structure of the cosmic web was well established. Galaxy clusters were assembling. The universe was transitioning from the rapid changes of its youth to the more sedate evolution characteristic of its middle age. This maturation continued over the following billions of years. By 7 billion years after the Big Bang, when the universe was about half its current age, it had taken on many characteristics we see today. Spirals and ellipticals existed in roughly their current proportions. The rate of major galaxy mergers had declined. Star formation, while still ongoing, was much less vigorous than during the peak era billions of years earlier. In the last several billion years, the universe has entered what might be called its late adulthood. Star formation continues to decline. The supply of cold gas that fuels star formation is gradually being depleted as it's converted into stars, or heated by various feedback processes. The universe is still expanding, and that expansion is accelerating due to dark energy, which will ultimately determine the universe's far future fate. Today, 13.8 billion years after the Big Bang, we observe a universe filled with diverse galaxies in various states. Some are still actively forming stars, though at modest rates compared to their ancestors billions of years ago. Others are red and dead, having exhausted their gas supplies. Some are isolated field galaxies, while others cluster together in groups and massive clusters. Mergers still occur, but are less common than in the past. The cosmic web is mature and well-defined. Looking to the future, simulations and models predict continued evolution. Over the next few billion years, star formation will continue to decline. More gas-rich spirals will transform into gas-poor lenticulars and ellipticals. In dense environments, galaxy mergers will continue, gradually building up the most massive elliptical galaxies at cluster centers. On even longer timescales, tens or hundreds of billions of years in the future, star formation may cease entirely as all available gas is consumed or blown away. Existing stars will gradually die, with the longest-lived red dwarf stars lasting for trillions of years. Eventually, galaxies will consist entirely of stellar remnants, white dwarfs, neutron stars, and black holes, along with the dimmest, coldest brown dwarfs. The universe will become darker as its remaining light sources gradually fade. But these far future considerations remain speculative. What's clear is that the galaxies we see today are products of 13.8 billion years of evolution. From the first tiny proto-galaxies formed in the first few 100 million years to the mature systems we observe scattered throughout the cosmos. Each galaxy carries within it a record of that history, encoded in its stars, its structure, its chemical composition, and its relationships with its neighbors. Despite the tremendous progress in understanding galaxy formation over the past few decades, many mysteries remain. The James Webb Space Telescope has answered some questions while raising new ones, and there are fundamental aspects of galaxy formation that we still don't fully understand. One of the biggest mysteries concerns the nature of dark matter itself. We know it exists, we know how much of it there is, and we understand its crucial role in galaxy formation. But we still don't know what dark matter is made of. Is it a new type of elementary particle, perhaps weakly interacting massive particles called WIMPs? Is it axions, hypothetical particles proposed to solve other problems in physics? Or is it something else entirely, perhaps primordial black holes formed in the very early universe, or some exotic form of matter we haven't even thought of yet? Despite decades of increasingly sensitive experiments, dark matter particles have not been directly detected, making this one of the most important unsolved problems in physics. The first stars, population 3, remain entirely hypothetical. We've never directly observed one because they existed so long ago and lived such brief lives. All our knowledge about them comes from theoretical models and indirect evidence. Did they really form with the masses we predict? How many formed? How long did they last? What fraction of them ended in different types of supernovae versus forming black holes? James Webb might be able to detect the signature of population 3 star formation in the spectra of very distant galaxies, but so far definitive detection remains elusive. The formation of supermassive black holes in the early universe remains puzzling. How did black holes containing billions of solar masses form so quickly? What were the seed black holes? How did they grow so rapidly? The discovery of increasingly massive black holes at increasingly early times continues to challenge our models. It's possible that our understanding of black hole accretion in the early universe is incomplete, or that there were formation mechanisms operating then that don't occur today. The exact timeline and mechanisms of reionization are still being refined. While we know it began around 200 million years after the Big Bang and was largely complete by about 1 billion years, the details remain uncertain. What were the relative contributions of different ionizing sources? How did the process vary in different regions of space? What role did the first black holes play? How did reionization affect the subsequent formation of low-mass galaxies? The relationship between galaxies and their environment continues to reveal surprises. Why do some galaxies in clusters continue forming stars while others don't? What determines whether a galaxy maintains its disk structure or transforms into an elliptical? How do galaxies acquire their gas and what processes regulate that acquisition? The details of ram pressure stripping, tidal interactions, and other environmental effects are still being worked out. The very early galaxies discovered by Webb have raised questions about galaxy formation efficiency. The theoretical models that worked well for explaining galaxies at later times may need adjustment to account for the apparently rapid formation of massive galaxies in the first few 100 million years. This could point to new physics, or it might simply mean that we need to better understand the efficiency of star formation and black hole growth under the extreme conditions of the early universe. There are also questions about the ultimate fate of galaxies in the far future. Will the local group, consisting of the Milky Way, Andromeda, and dozens of smaller galaxies, eventually merge into a single giant elliptical? What will happen to other galaxy groups and clusters? How will the accelerating expansion of the universe, driven by dark energy, affect the long-term evolution of structure? These questions extend billions of years into the future and depend on understanding dark energy, another mysterious component of the universe that we know exists but don't truly understand. The role of magnetic fields in galaxy formation is another area where our understanding is incomplete. We know that magnetic fields exist in galaxies and in the intergalactic medium, but we don't fully understand how they formed, how they evolved, or exactly what role they play in regulating star formation and driving galactic winds. Recent simulations that include magnetic fields show that they can have significant effects, but matching these simulations to observations remains challenging. We've traveled an extraordinary distance tonight. We began at the very start, in those first fractions of a second after the Big Bang when the universe burst into existence. We watched as it expanded and cooled, as the first atomic nuclei formed in the primordial fireball, as recombination made the universe transparent, and as the dark ages descended. We saw how dark matter began, its patient work during those dark ages, accumulating into halos that would become the gravitational scaffolding for all future galaxies. We witnessed the ignition of the first stars, those massive population 3 giants that lived fast and died spectacularly, seeding the universe with its first heavy elements and ending the cosmic darkness. We followed the epoch of rionization, as those first stars and galaxies transformed the universe, creating bubbles of ionized gas that eventually overlapped and filled all of space. We saw the first true galaxies emerge, small irregular systems that would serve as the building blocks for everything that came later. We explored how the James Webb Space Telescope has revolutionized our understanding of these early times, revealing galaxies that formed just a few 100 million years after the Big Bang and challenging our theories with their surprising brightness and maturity. We learned about the diverse types of galaxies that evolved over billions of years through mergers, interactions, and steady growth. Spirals with their graceful arms, ellipticals with their ancient stars, and irregular systems still shaped by ongoing chaos. We delved into the mystery of supermassive black holes, those gravitational monsters that grew remarkably quickly in the early universe and came to play crucial roles in regulating their host galaxies. We zoomed out to see the cosmic web, that magnificent large-scale structure that organizes galaxies into filaments, sheets, and clusters separated by enormous voids. We trace cosmic history from the Big Bang, through cosmic dawn, through the era of peak star formation, into the mature universe we see today. And we acknowledge the many mysteries that remain, the questions that future generations of astronomers will work to answer. The story of galaxy formation is ultimately the story of how the universe organized itself from simplicity to complexity. From an almost perfectly uniform sea of hydrogen and helium gas, gravity sculpted a cosmos filled with intricate structures on every scale. The tiny quantum fluctuations from the universe's first moments grew into dark matter halos, then into galaxies containing hundreds of billions of stars, then into the cosmic web spanning billions of light years. It's a story that continues today. Somewhere out in the universe right now, stars are being born in the nebulae of distant galaxies. Galaxies are colliding and merging, their shapes being transformed by gravitational encounters. Gas is flowing along cosmic filaments toward galaxy clusters. Black holes are growing, winds are being driven, and new elements are being forged in the hearts of dying stars. The universe is still evolving, still changing, still writing new chapters in its ongoing story. And we're privileged to be here to witness it, to study it, to try to understand it. Every observation from a telescope, every computer simulation, every theoretical calculation brings us closer to comprehending this magnificent cosmic saga. The galaxies we see scattered across the night sky are not just beautiful objects. They're time machines carrying information about the history of the universe. They're laboratories where we can study physics under conditions impossible to reproduce on Earth. They're markers showing us how matter organizes itself under the influence of gravity across cosmic time. The light reaching our telescopes from the most distant galaxies began its journey when the universe was young, less than 1 billion years old. That light has been traveling through space for more than 13 billion years, stretched by the universe's expansion from ultraviolet into infrared. When we observe these ancient galaxies, we're not seeing them as they are now. We're seeing them as they were, frozen in time, showing us a universe that existed in the distant past. Those galaxies, if they still exist today, have evolved beyond recognition. The small, irregular proto-galaxies detected by Webb have probably merged and grown into large spirals or ellipticals by now. But we can't see their present state because the light showing what they look like now hasn't reached us yet. It won't arrive for billions of years. This is one of the profound aspects of cosmology. The expansion of the universe means that we can see its history directly, looking back in time by looking at distant objects. The universe is so vast and so old that light itself becomes a time machine, and telescopes become not just instruments for seeing far away, but instruments for seeing far back in time. The galaxies we have discussed tonight represent just a fraction of what exists. The observable universe contains roughly 200 billion to 2 trillion galaxies, depending on how you count small, faint dwarf galaxies. Each one is unique, with its own history, its own population of stars, its own quirks and characteristics. Some are active and star-forming, others are quiescent. Some have recent merger histories written in tidal tails and disturbed structures. Others have evolved in isolation for billions of years. Some host active black holes with jets shooting out across intergalactic space. Others contain dormant black holes, quiet and unseen. And beyond the edge of the observable universe, there are surely more galaxies, forever out of reach, because their light will never have time to get to us. The universe is larger than the part we can see, possibly infinitely larger. Those regions beyond our cosmic horizon have their own galaxies, their own stars, their own planets, their own stories. We'll never see them, never know about them, never understand what's happening there. But they exist nonetheless, products of the same physical processes that created the galaxies we can see, formed from the same primordial elements, shaped by the same forces of gravity and radiation and cosmic expansion. This vastness can be overwhelming. The scales involved, both in space and in time, stretch human comprehension to its limits. 13.8 billion years is a period so long that we struggle to truly grasp it. When the first galaxies were forming, roughly 13 billion years ago, about the same amount of time has passed between then and now, as passed between now and when the last dinosaurs walked the Earth times 300. The distances are similarly staggering. The farthest galaxies Webb has detected are so distant that their light has traveled for over 13 billion years to reach us, crossing a space that has expanded to billions of light years in the meantime. Yet despite these vast scales, everything we see in the universe follows the same physical laws. The gravity that makes an apple fall on Earth is the same force that pulls galaxies together across billions of light years. The nuclear fusion that powers our sun powers every star in every galaxy throughout the cosmos. The quantum mechanics that governs atoms in our bodies govern the behavior of matter in the early universe. This universality of physical law is what makes cosmology possible. We can study distant galaxies and understand what's happening in them because the same physics applies everywhere. The journey from the Big Bang to galaxies is really a journey from symmetry to complexity. The very early universe was remarkably simple and uniform, just energy and the simplest forms of matter, nearly identical in every direction. But tiny imperfections, quantum fluctuations amplified to cosmic scales, broke that symmetry. Gravity amplified those imperfections, pulling matter together, creating structure. Each step added new layers of complexity. Dark matter halos formed. Gas fell into those halos. The gas fragmented, stars formed. Stars exploded and enriched the gas with new elements. More stars formed from that enriched gas. Galaxies assembled through mergers and accretion. Black holes grew and began shaping their host galaxies. Galaxies clustered together along the cosmic web. And after billions of years of this hierarchical process, we arrive at the rich, diverse universe we see today. It's a universe where complexity has emerged from simplicity through the action of physical laws playing out over vast periods of time. And remarkably, that complexity includes us. We are products of this cosmic evolution. The atoms in our bodies were forged in the hearts of stars, distributed through space by supernovae, and eventually incorporated into planets around later generations of stars. We are, quite literally, made of stardust, the heavy elements created by nuclear fusion and stellar death in galaxies throughout cosmic time. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created inside stars and dispersed into space when those stars died, then incorporated into new clouds of gas, from which new stars and planets formed, eventually including the Sun and Earth and us. This connection between cosmic history and human existence is profound. We're not separate from the universe, observing it from outside. We're part of it. We're how the universe has come to know itself. The atoms in our brains were formed in stars billions of years ago. Those atoms have arranged themselves, through the long process of cosmic and biological evolution, into structures capable of studying their own cosmic origins. We are the universe made conscious, matter that has learned to contemplate matter. The study of galaxy formation is therefore more than just astronomy. It's the study of our origins, our cosmic roots, the long chain of events that made our existence possible. When we look at images from the James Webb Space Telescope showing galaxies from the early universe, we're seeing the universe as it was when the material that would eventually become the Milky Way was still scattered among thousands of small proto-galaxies. When we study how galaxies form and evolve, we're learning about how our own galaxy formed and evolved. When we investigate how stars create heavy elements, we're learning about how the elements necessary for life came to exist. Before we close, remember that if you enjoyed this journey through cosmic time, if these stories of dark matter and first stars and assembling galaxies resonated with you, please take a moment to like this video and subscribe to Nebula Nights. Your support helps us continue exploring the wonders of the cosmos together, bringing you more deep dives into the universe's most fascinating phenomena. Hit that notification bell so you never miss our next journey through the stars. The universe is still revealing its secrets. Every new observation, every new mission, every new generation of telescopes brings fresh surprises and deeper understanding. The galaxies scattered across space are not static museums, but dynamic, evolving systems that continue to teach us about the cosmos. Their light carries information across billions of years, whispering to us about the early universe, about the nature of dark matter, about the birth of stars and the growth of black holes, about the structure of space-time itself. As we close tonight, take a moment to think about what we've explored. Imagine yourself floating in the darkness of space, looking back toward the first moment after the Big Bang. Watch the universe expand and cool. See recombination turn the universe transparent. Witness the dark ages descend. Then see the first stars ignite, small points of light appearing in the darkness. Watch as they multiply, as galaxies form around them, as structure grows and the cosmic web emerges. See galaxies merge and collide, transforming their shapes. Watch supermassive black holes grow at galaxy centers. See the universe fill with light as billions of galaxies form, each one a vast collection of stars. Then bring yourself forward through time, through billions of years as those first small galaxies grow, emerge, and transform, as the universe evolves from its turbulent youth into the mature cosmos we observe today. And finally, arrive in the present moment, looking out at a universe filled with 2 trillion galaxies, each one with its own story, each one a chapter in the great cosmic narrative that began 13.8 billion years ago and continues today. This has been Nebula Nights. Thank you for joining me on this journey through the birth and evolution of galaxies. Until next time, keep looking up at the stars and keep wondering about the universe that made them and us possible. Clear skies.